and be a co-host or something.
Say that again.
I said, I see you, but I don't see many other people, so.
I'm excited to hear you speak.
Thank you.
All the best.
Thanks.
All right, I'm going to turn it over to you, Helena, for the intro. Thank you.
Yes, thank you. So welcome to our Geospatial Forum. Thank you all for coming. And let me introduce our speaker, Dr. Antonia Sebastian. We will talk to her, call her Tony here. I hope that's okay. Yeah, so Tony is an assistant professor at the University of North Carolina at Chapel Hill, where she holds appointments in both the Department of Earth, Marine, and Environmental Sciences and the Environment, Ecology, and Energy program. Tony holds a PhD and bachelor's degree in civil and environmental engineering from Rice University. Prior to joining UNC, she was associate research scientist at Texas A&M at Galveston, where she served on the Governor's Commission to rebuild Texas after Hurricane Harvey and helped to establish the Institute for Texas Disaster Resilience. These are efforts that are highly relevant to the NC State Coastal Initiative. So it's great to really have you here. Tony's research involves the application of interdisciplinary methods in socio-hydrology and engineering with focus on evolution of flood risks in response to changing human and environmental conditions. Her presentation will highlight recent findings from urban flood studies in the Houston-Galveston region with a specific emphasis on changes in runoff patterns caused by climate and land use dynamics. We will do the questions after the presentation, but please, you are welcome to post your questions in the chat. And welcome, Tony. And now the Zoom is yours.
Thank you, Helena. It was very nice introduction, and I'm really excited to be here. I'm a little bit sad not to be in person. I moved to the Triangle in 2020, so I'm relatively new to the area, or I say I'm COVID new to the area. So I know a few people in the room, but not everybody. And I really look forward to the opportunity to meeting people in the future. I thought a lot about what I could talk about today, and what I decided would be the most interesting and perhaps the most relevant was thinking a little bit about Hurricane Harvey and the landscape evolution that's happened in Houston over time, and some of the modeling that we've done to try to understand how that landscape evolution has affected flood risks with a specific focus on Hurricane Harvey. So I'm going to spend some time talking about the history of Houston and talking about case study results for Harvey, and then I'll briefly mention some policy relevance of the work that we've done and some changes in policy around flooding in the state of Texas, and then sort of transition into some of the things we're thinking about in North Carolina and that my lab group is working on, if there's a little bit of time at the end, which I hope there is, to showcase some of the student work in my lab. So I titled this talk, Attributing Flood Hazards to Anthropogenic Change, but it's a kind of a combination of environmental and anthropogenic change in the Houston area. And so maybe as a starting place, we can talk about the fact that Houston's history is fairly short. So Houston's only been around since 1836, but its history is really tied tightly. Its economic history and its flood history are tied tightly together. So this is sort of a plot that I stole from the Harris County Flood Control District, showing major events over time, and we'll go through it in a little bit more detail, so don't feel like you have to read it all right now. But sort of the key thing here is these are decadal time steps, major events that are happening, and the growth of the population of Houston in green, shown here in the background, over the same time period. And so, as I mentioned, Houston's economic history is tied really tightly to its flood history. And if we sort of go through some of these major events that have happened, we can talk about the responses that have enabled Houston to continue to grow. So in 1900, there was a major hurricane that made landfall in Galveston. To date, it's still the deadliest hurricane in US history. It killed about 8,000 people. And in response, Galveston Island built a 17-foot seawall to protect it from the shore. But it also prompted the decision and federal funding for the Houston Ship Channel. So the goal here was to move the economic center of the Texas coast further inland where it could be protected from surge. And so if we look at what this kind of looked like, here's some pictures post-Galveston hurricane. It's worth noting there was another one in 1950, but right after the first one, they elevated the island to 17 feet, and they did this by raising up any houses that were left standing and backfilling underneath them with dredged material. And here on the right-hand side, you can see the ship channel at the time that it was constructed. They moved it inland. The primary economic resources at the time were timber. So they built the ship channel in order to be able to more easily ship timber, but also to develop a city that was protected from storm surge further inland. And you can see the Houston Ship Channel today. So this was sort of a critical moment in the development of Houston. And you can see early on, population was really low, and then it rapidly began to grow. In the 30s, there were a couple of major flood events, primarily brought on by heavy rainfall. Kind of a landmark event was this 1935 storm, which I'm going to come back to later in the presentation. And it caused record flooding along Buffalo Bayou. About 50 feet of water in downtown Houston were observed. And it led to the creation of the Harris County Flood Control District, which many of you have probably heard of. They're instrumental in sort of the management of flooding in Houston to this day. They govern, or they have jurisdiction over all of the water bodies in the city of Houston, and they work closely with the Army Corps of Engineers. And sort of in the period after the 30s, we saw a huge amount of construction related to flood control. So between 42 and 48, they built 2 large dams to the west side of Houston to protect the downtown area. And in the 50s, many of the bayous across Houston were straightened and channelized. So here you can see sort of a pre-straightened bayou and a post-straightened bayou, and you can see the channelization, which is usually in some form of concrete lining and straightening. And what's important to note here was that at the time that these reservoirs were constructed, no one ever thought Houston would get as big as it was, or as it is today. So these reservoirs were constructed about 30 miles west of downtown, but they really enabled the city to grow westwards because of the protection that they provided for all of the structures in between them and the downtown area. This was followed by a couple of hurricane events. One that is worth noting is Hurricane Carla. It was the largest hurricane in US history, prompted the construction of the Texas City Levee and Dike. The plans were already in place, but having a hurricane really allows you to get some additional federal funding. So the Texas City Dike was built here, and that's allowed the city to continue to grow towards Galveston. And a couple of more storms. Claudette is worth noting. At the time, it was the highest one-day rainfall. Alicia was the costliest tropical cyclone in history at the time. And then we get sort of to our present day 2000s period. And the 2000s have really been punctuated by many, many flood events. So there are plenty of storms in between all these flood events that I'm noting here, but these are the major events that cause a lot of damage. Some notable storms were Allison in 2001. It was the costliest tropical storm at the time and the largest urban flood in history. I'm sure that's been exceeded not only by Harvey, but also potentially by Ida now. And Ike, which was a surge-based event and the 3rd costliest tropical cyclone in history. And these 2 storms also had significant impacts on flood management in the Houston area. Allison led to the Tropical Storm Allison Recovery Project, which was really one of the first large-scale flood hazard mapping projects using new technologies like LIDAR digital elevation, radar rainfall data. So this was a big advance in our data for floodplain mapping. And it also led to some projects, one called Project Braze, which is a $500 million project to extend some of the channelization that had happened in the bayous in the 50s to account for additional development, but also some small scale adaptation and protection of critical infrastructure around the city. And Hurricane Ike is significant because it really started conversations around additional surge protection for the region. One of the projects is known as the Texas Coastal Spine. Some of you might have heard of it. Conversations around these projects are ongoing primarily because of their cost and scale. And then came the 2010s. And the 2010s were just a giant mess with respect to flooding, primarily or specifically events that happened in 2015, 2016, and of course, 2017. And so, the history of flooding in Houston sort of culminates with this 2010 active flood period that brings us to Hurricane Harvey. It's probably worth noting there's another event, Imelda, that happened in 2019, but we're sort of going to end our story with Harvey here. And Harvey was really significant. It made landfall near Rockport on August 25th as a major hurricane, so as a Category 3 hurricane, really high winds, plenty of storm surge down here in the southern Texas coast. But as it moved inland, it was rapidly degraded into a tropical storm and then later a tropical depression. And the key thing about Harvey was that it stalled out over land. And it took many, many days to move across the state. And that caused it to drop an enormous amount of rainfall over the Houston-Galveston region and Beaumont. It was record-setting, like many of the storms for the Houston region have been. It holds records for the highest tropical cyclone rainfall event ever recorded. So we recorded about 61 inches of rain from this storm in the area between Houston and Beaumont. It accounts for the largest number of direct deaths from a tropical cyclone in Texas since 1919. So there were 68 direct deaths and many indirect deaths. And it's the highest 5-day rainfall over both a 1,000 square mile area and a 10,000 square mile area. And many gauges across the state, actually across the region, not only in the Houston area, reached record peaks that had not been seen before. And it represents the largest disaster response in Texas history and estimated to have impacted upwards of 13 million people. And like many storms, I think we're all really familiar with the flood pictures that come out of the events. Here is one in the wake of Harvey. Harvey was a significant pluvial flood event. So because of the intense rainfall, we saw widespread flooding really far from waterways in Houston. These are called bayous. And many, many people were displaced or experienced flooding in their homes. And there were several million cars that were damaged. So you had a lot of people walking around after the storm. And there were also a huge number of high water rescues. So upwards of 10,000 high water rescues were conducted by the Army, the National Guard, local emergency response agencies, as well as the Cajun Navy, which is a volunteer organization. And so these pictures came out after the event, like they do after many events. And what's probably worth noting is that for myself, at the time, I was living in the Netherlands. And so I was kind of watching this from afar, having studied Houston for many years during my PhD already, and really wondering, or really somewhat shocked at the scale of this storm compared to what I had seen before. And I think many other people felt the same way. And while in the Netherlands, I was approached by a couple of colleagues from the World Weather Attribution, which is a nonprofit scientific organization whose goal it is to rapidly attribute impactful weather events to anthropogenic climate change. And I was approached by a colleague of mine who I had collaborated with before, as well as Freddie Otto and Gert-Jan van Oldberg, who recently passed away of cancer. And what their organization does and why they approached me was that they are interested in doing these attribution studies, but they also often want to have somebody on the team who knows something about the exposure and the vulnerability on the ground. So placing some of the work in context. So I will be the first to say I'm not a climate scientist, but I'm going to try to convey some of the results of our project and explain how it leads up to some of the hydrology work that I did afterwards. And so, as we've mentioned, Harvey was somewhat unprecedented. And if we look at some of the rainfall that was observed during Harvey and relate it to what has been historically seen at gauges around the state, we estimate that in the current climate, Harvey was an extremely rare event. Based on the gauge where we saw the maximum rainfall in Baytown, Harvey was about a 1 in 9,000 year event. And at many great gauges across the region, Harvey exceeded a 1,000-year event. So even in the current climate, Harvey was sort of unprecedented. And these attribution studies, or the way that our attribution study worked, was that we collected a combination of gauge rainfall data and other types of observed rainfall data and data out of climate ensemble models, and used them to estimate the likelihood of Harvey in the current climate and in a counterfactual no global warming scenario. And so we just specifically about some of this data, we had about 30 years, we had about 85 gauges with greater than 30 years of data and 13 gauges with greater than 85 years of data to use. We also relied on a gridded CPC database that had a 25-kilometer resolution of observed rainfall data. And then the study used 3 different ensemble climate models, but this ensemble climate model could not do a very good job of representing the tropical rainfall event. So it ended up getting thrown out of the results. And as I mentioned, the method, or like the key goal here, is to examine the event in the current climate and in the counterfactual climate. And the way that we do this, or the way that they did this, because I definitely was not the one running the models, was to compare the event to a generalized extreme value distribution scaled for that global warming. And what the study found was that the 3-day precipitation intensity from Harvey, or what we concluded, I'll back up, based on all of these different data sets, was that global warming conclusively made Harvey's precipitation about 15% more intense, or if we think about that in terms of probability, Harvey was about 3 times more likely to occur in the current climate than it was in the historical climate. And these results for our study fall in line with a couple other studies that came out in the probably week or 2 before or after this study. So the goal of these are really rapid attribution, scientifically sound methods, but several of these studies came out sort of simultaneously that said all about the same thing. The results also generated like a huge amount of press. So the New York Times was citing it, National Geographic was talking about it, because there had been a couple of other attribution studies before this, but this was one really caught the media's attention. But for me, it didn't really answer my question. So just to back up, the reason that I was involved in this is I had some local knowledge of what was going on in the ground in terms of hazard exposure and vulnerability. And I was really asking questions around what was the role of urbanization in causing the flooding that happened during Harvey. So if we look at some of these plots here on the right-hand side, these are 4 different gauges across the city. And these are annual stream flows that have been observed at these gauges over time. So mostly since about 1930s. And we see that the annual, I mean, visually, we can just see, we don't even have to run any statistics to see that over time, the annual discharges, or the maximum observed annual discharges, have been increasing. And I was asking the question of, like, does climate explain all of this, or are there other things that we can disentangle from climate to understand what's happening across the city with respect to flooding over time? On the left-hand side of this plot, you'll see a figure that I put together actually just last night, somewhat similar to our timeline at the very beginning. So this blue line is the same as what was on the green line in the timeline before, and it shows the population growth in Houston over time. And here I've started the plot in about 1938. And I pulled some land use data that wasn't available at the time that I did the study, but is available now. It's a historical backcasting of land use for the Houston area, or for the whole CONUS, but I pulled out some data for the Houston area. And what we can see is that as urbanization has increased over time, natural and agricultural land has decreased. And we know as hydrologists, and maybe as the general public at this point, that urbanization generally increases runoff because it decreases roughness over the landscape, and it also decreases the amount of, or the volume of water that can be infiltrated over the landscape. So we kind of expect that as urbanization increases, we're going to see additional runoff, and we're going to see faster and peakier runoff. So we're expecting that as urbanization changes, we're also seeing increases in flooding. And so in order to do this disentangling the role of urbanization with respect to climate change for Hurricane Harvey, we really needed to reconstruct sort of a counterfactual environment for the 1900s, no climate change, no urbanization condition in which we could model Harvey. So our goal was really to create two scenarios. It actually ended up being a lot more scenarios, but really to be able to create two hydrologic models, one for 1900 and one for 2017, so that we could turn things on and off in the model to understand the roles of urbanization and climate change. And the primary challenge in doing this was really to generate that historical model and find some data with which we could validate it. So just to take a moment to talk about the landscape of Houston, this is a map of the San Jacinto Buffalo Bayou watershed. It's a Huck 8 watershed, and it drains most of what is important for downtown Houston. It's important to note that there can be interbasin transfers from this small creek up here into Buffalo Bayou watershed, and that did happen during Harvey, and it was something we couldn't represent in our model. So I'll talk about that again at the end. The Addicks and Barker dams, which I've mentioned a few times, are located here in this hatched area. And you can see the estimated or the approximate extent of the city of Houston in the early 1900s and the extent of the jurisdictional city of Houston today. Houston itself, of course, is like urban sprawled out to, I don't know, here somewhere. So just thinking about these jurisdictional areas for the map was worthwhile. The city of Houston, or this watershed, Harris County's jurisdictional area has 21 bayous in it. Many of them are within this watershed. And a bayou, for those of you who don't know, it's very like southern Gulf Coast word. A bayou is a stream that is rainfall fed and has, it's fairly brackish because it's tidally influenced. So they are not spring fed, they're not flowing rivers, they're really these sort of rainfall, marshy rainfall gullies. And in the historical environment before development occurred, they were quite wooded. And so in order to create this historical reanalysis, we had to sort of back up to this 1900s environment and try to figure out how to represent it. And we did this using a whole lot of aerial imagery, and I'm not a remote sensing person, so this is probably maybe cringy to some of you, but we used a lot of so we had some data from 1940 about different land use polygons, and we were able to use that data combined with old historical imagery to sort of remap where we thought the forested areas were, the agricultural areas, and the little bit of urbanization that existed in early 1900. And this is just sort of an example of one of these maps that we had access to from the state archives. And you can see sort of the extent of some of the developed areas, but also sort of these wooded areas around the channels at the time. We also had in our possession a distributed hydrologic model. So this is for the hydrologists in the room, and I'll give some hints for the non-hydrologists in the room. We had access to this distributed hydrologic model, which we'd actually built for another study, and called VFlow. And VFlow was developed by Baxter Views in the late 80s and 1990s, and it's it uses finite element scheme to solve the kinematic wave equation for overland routing. And channel routing can also be solved via the kinematic wave, but there's also a couple of other solvers that the model has in it. And for those of you who are interested, it also has green and amp, so it has temporally and spatially varying infiltration parameters included in it. And the model takes into consideration high resolution land use land cover, high resolution soils data, and a digital elevation model to generate sort of a flow path and estimates of infiltration, and then you route it via this channel network of overland and channel cells through the environment. Some of the unique features of this model are that it includes a high resolution channel subgrid, so you can cut cross sections or you can import cross sections, for example, from HEC-RAS models. Reservoirs can be represented in this model using stage storage relationships. It takes in gridded precipitation, particularly gauge adjusted radar rainfall, and we validated it across several studies for the Houston region. So there's lots of examples of this model being used in Houston already. That was just sort of an aside. So let's talk about how we validated our pre-development and post-development model. So one of the things we had to do, as I mentioned now, is that we built this model to represent Houston in the 1900s. We recreated the historical land use, land cover, and increased channel roughness to represent pre-development conditions. And what we were really interested in doing was figuring out or validating this model against a real event so that we could be somewhat confident that it could represent historical conditions. So the goal here was kind of turning back the clock, my little schematic here, turning back the clock on development. Unfortunately, but also fortunately, so unfortunately, there's not a lot of data for historical flood events that go back that far. But fortunately, we did find one report, this Dalrymple report from 1937. 1935 was a really significant year in Texas. There were lots of floods, and there was actually a statewide flood report that was written with lots of data in it. So we were able to find one calibration event to use for our early 1900s model. And in this report, we found rainfall data at 12 locations throughout the city, so we could, or throughout the watershed, so we could sort of replicate a storm. And there was also one outflow hydrograph that had been measured. I believe somebody went out and took measurements like hourly or 6 hourly. So we had pretty decent hydrograph data to compare against. And there were also 4 additional observed discharge points throughout the city. And so for the non-hydrologists, what we're looking at here is that there is a plot of the modeled output here in dark black, and then there is a dotted line that represents the observed data that was in the report. And for, again, for non-hydrologists, what we're really looking for is how closely do we match this peak and how well do we match the shape and the timing of this curve. And given the sort of potential uncertainty in this data and the potential uncertainties in the approach that we took to create the landscape for the model, we thought that this was actually a pretty good representation. Also, when compared against the 4 points, peak discharge points that we had access to, our model performed pretty well in terms of peak discharge. So we were satisfied. We also had to do something similar for the current climate. And for this, we actually had plenty of data, and we focused on 3 recent storm events. So these occurred in 2015, 2016, and 2016, as well as Hurricane Harvey. And we had gauge adjusted precipitation, so lots of great data for the current climate to compare against. And our model performed fairly well. However, so fairly well for this 2015 storm and this 2016 storm. We didn't perform as well for this May 2016 storm. We had an R-squared of 0.55, but this was a much smaller event. And since Harvey was such a large event, we were more concerned with performing well against the large event. So for the non-hydrologists, this is a plot showing the, again, the modeled versus the observed hydrographs. This is actually a point for Hurricane Harvey. And what's worth noting here is that when you have events with multiple peaks, they tend to be really, really hard to match with hydrologic models. So this is actually quite a good match for a multi-peak storm event. So enough about the modeling. Let's talk a little bit about what we ended up doing with these models. So again, we had sort of 2 models. We had a 1900s scenario model, and we had a 2017 scenario model. And what we could do with these models in each of them was turn things on and off. And what we were interested in turning on and off were climate change and land use. And we were also interested in isolating the effects of those reservoirs that had been built so that we could actually do some large scale statistics at the end. And so we came up with sort of 6 scenarios that I'm going to show you in the next couple slides. A climate change only scenario, a development only scenario, and one where we had both on. So this is sort of a current conditions. Well, this one's sort of a current condition scenario. And we modeled all 3 of these for both the situations in which we had no dams and dams built. And these are what the results look like. So the dots here represent USGS gauges, which were the points that we chose to model output at. And sort of what you take away here is that precipitation, these are all relative to a 1900s baseline scenario in which there's no precipitation, no development, nothing has happened. And so here we can see slight increases in color due to the increase in precipitation, even greater increases due to development alone, and the greatest increases due to their combined effects, which is no surprise. What I do want to point out is that the largest changes in the development scenarios occurred in areas that were just downstream of channelized portions, which I kind of highlighted here in gray. And what I also want to point out is that downstream, or let's put it a different way, even though these reservoirs were opened during Harvey and water was released, if you compare them to the situation without reservoirs, they provided significantly reduced flows in areas downstream of the reservoirs. So just as a small aside, these reservoirs are significant flood control structures for the city of Houston. Let's look at this another way. So we were also interested in sort of aggregating or looking at these results across the whole study region. And these results are shown here in the situation or in the model runs without any reservoirs in place, because it allowed us to more accurately represent the roles of the landscape change and the climate change. And so some key takeaways from these plots. We looked, let me back up just real quick. We looked at sort of 3 things, or we were interested in 3 things as flood modelers. One was how much is discharge changing, so peak flows. We were also interested in changes to volume. And finally, we were interested in the change in the timing of the discharge of these events. And so if we look across these 3 things, we saw here that climate and development increased peak discharge by about 1.8 times relative to our baseline scenario. We saw that development didn't really have a significant impact on volume, but increasing precipitation yielded about an 18% increase in volume. So this was almost a linear increase in the volume of water that's running off from these storms. And then finally, climate and development decreased time to peak by about 13 hours. And this is significant because it reduces your time to respond to an event. So we're interested. It also means that the event is much flashier. So just some key findings and takeaways from what we saw in this study. We saw that changes were largest in parts of the watershed that had experienced channelization. We observed some attenuation of peak discharge at larger scales. So on that last plot, the dots were sized by the contributing area to that gauge location. And so we saw that peak discharge was somewhat attenuated when you move across larger and larger scales, but the opposite was true for the volume observations. This is somewhat significant because it sort of hints at understanding the scale at which some of these urbanization processes are impactful. So tributaries might be severely impacted by rapid urbanization, whereas the larger systems may see a little bit less effect of urbanization. It gets attenuated within the system. And then what I was really excited about, or what my take-home message was that we saw a loss of adaptive capacity across the entire system due to the development that had occurred. And we observed this because we saw that the equivalent increase in precipitation for the 1900s versus the 2017 yielded much larger results for the 2017 scenario than for the 1900 development scenario. So for 1900 conditions, a 15% increase in precipitation increased flood peaks by 20%. And in the 2017 scenario, it increased them by 31%. And so this also gave us sort of the inkling or suggested that the cumulative impacts of climate and development were much larger than the sum of their individual parts. And for me, this raised even more questions, as it should as a scientist, about the role of channelization and urbanization patterns in Houston. So I'm just going to briefly mention another study that we had ongoing somewhat simultaneously. We were asking this question about whether or not some types of flood mitigation and flood control strategies might be maladaptive over the long term. Lots of literature or lots of discussion that suggests channelization is not resilient over long timescales. And so we were comparing two neighboring watersheds in the city of Houston that are similarly sized and have very similar characteristics. So this is a map of their soil characteristics, and this is a map of development across these two watersheds. And the key difference between them is that in Buffalo Bayou up on top, there is quite a bit of buffer away from the channel, and the channel has been left mostly in its natural state. And downstream, or in Brays Bayou, the channel is extremely straightened and very much channelized, and there is no buffer to the stream itself. Otherwise, they're similar in size and other properties. And so you can kind of see the differences here. Here is Buffalo Bayou, which there has been a little bit of straightening, but generally it's fairly natural. And this is Brays Bayou, which is very channelized. And they've also been experiencing similar patterns in development over time. And so we were interested in looking at, relative to their channel structure, how has development influenced flooding over time in these two watersheds. We used similar methods to the previous study with respect to the hydrologic model, but we also added HEC-RAS in here so we could actually map some floodplains. And what we saw was that if we looked over the last 40 years, so if we compared 2011 to 2016, I think was the period, 1970 to 2011 and 2011 to 2040. Between 1970 and 2011, we saw a 5-fold increase in the size of the 100-year floodplain in the Brays Bayou watershed, which is very, very channelized. And sort of this indicated that over long time periods and in the face of rapid urbanization, these channel structures may be less resilient to upland changes. It's probably worth noting, and in the paper we talk about this a lot, that this channel has a lot more capacity, and also I think because it is so windy, it has more ability to attenuate the flooding as well. So as Helena mentioned in my introduction, I was part of a governor's commission to rebuild Texas after Harvey. I mentioned I was in the Netherlands at the time that the hurricane happened, and I chose to come back to Texas to work on some of these policy pieces after the storm. And we made a couple of recommendations to the legislature and locally to the city of Houston, and many of them have been adopted. And they're similar to recommendations that I think have been made in the state of North Carolina and that many people are talking about here as well. So around watershed planning, it's very clear that historically development and mitigation practices didn't think about upstream downstream impacts. So the relationship, so watershed scale planning wasn't really a thing. You also have jurisdictions that cross watershed boundaries, and decisions made in one jurisdiction versus another don't really consider water so much as just jurisdictional boundaries. And so we recommended to the state that they take a watershed planning approach, and there's been a huge amount of budget set aside to do watershed planning for the state of Texas now. We also made some recommendations around building codes and infrastructure. Thinking about when designing infrastructure, for example, like in Brays Bayou, that you design for fully built out conditions so that you're not caught unawares when development occurs and your infrastructure is suddenly under-designed. And also thinking about setting building standards themselves to future storm events. After Hurricane Harvey, the city of Houston, I think actually Harris County adopted a measure to all new development inside the 500-year floodplain needed to be elevated. at a higher standard than what FEMA required. So there have already been some implementation of higher building code standards. And we talked a lot in the wake of Harvey about adding in sort of safety factors or buffers against climate, but also upstream urbanization. It's probably also worth noting, maybe as part of a watershed planning conversation, fill is really significant. Helena and I were talking about this just before the call, that as places urbanize, you actually have a significant impact on topography. And this is something that also needed to be considered in as part of the role of development, not just changes in roughness and infiltration. Sam Brody and Coyote Atoba at Texas A&M wrote a really interesting paper about buying them out before they're built. So just for reference, in Harris County, there are about 100,000 structures in the 100-year floodplain and maybe 300 in the 500-year floodplain. And so there's this conversation around how do we approach this, but also given that we're enabling and allowing people to continue to develop in floodplain areas, should we be setting aside undeveloped land that could act as buffer or that will be at risk in the future? And then finally, there were lots of recommendations about real estate disclosure. Texas is now one of the only states that requires you to disclose whether or not you've previously flooded when you sell your home, and more flood risk information. So there's some efforts going on with the Texas Disaster Resilience Institute to address this issue of providing more flood risk information. And Harvey I presented a couple of my own research things, but I do want to point out that Harvey has generated lots of cool and exciting research. There are several other papers. I kind of made note or mention of these. There's several other papers that have been written around climate change and flood attribution, including some that go all the way through to mapping pluvial and compound flooding. I also have a paper in this area, but also thinking about the economic costs or trying to understand the economic costs of climate change on flood extent, or how climate change impacted flood extent and what the economic costs of that additional flooding were. There are some people working on topics like tropical cyclone stalling and slowing down, so blocking patterns, so not just thinking about the change in precipitation, which is sort of a crude estimate of the impacts of climate, but also thinking about how climate might actually affect the hurricane characteristics or the meteorology of future storms. Pedram Hassan Zeta at Rice does this, and I think there's some really cool stuff coming out of his lab group. And then there are also a lot of people who've been writing around topics related to socioeconomic inequalities and development. Kevin Smiley is really active in this area. This is some work that Chris Hackenberg did, who was a UNC graduate student back in the day and then a postdoc at Rice, and he modeled annual changes in land use land cover in Houston. And he and Kevin together wrote a paper looking at who is actually represented by this land use change. So some of this work is really exciting. And then maybe I'll just as like another thing to note, the work that the rapid attribution that we did after Harvey really looked at changes in precipitation. And then I also did this study looking at runoff, but I think that kind of where we're at in terms of high resolution, large scale hydrodynamic models since 2017 has jumped leaps and bounds. And I think there is the potential that we will be doing rapid attribution in terms of hazard exposure and vulnerability, that is coming, being able to rapidly attribute all three of these things, and particularly risk in the wake of storms, to climate change and other drivers. I'll also say that Houston has just been like a really excellent place to study local, regional, and global scale processes. So all of the things that we talk about as increasing risk now and in the future are happening there, from sea level rise to increasing precipitation, to changing storm patterns, to rapid population growth and economic growth. These things have all been happening in Houston, which make it a really exciting place to study flooding over time. And maybe just like stepping out to the big picture stuff and talking a little bit about what my group is doing in North Carolina. And I'm gonna quickly look at the time. I think I'm okay. So we're seeing that despite investments in flood mitigation, damages and the costs of floods continue to increase. So there's this study, this famous study by Hogite, that suggests that global flood losses are expected to reach 1 trillion per year by 2050. And I think the study only considers sea level rise and population growth. So there's many other drivers. I bet this number is much, much larger. But in the US, a large fraction of the losses are occurring outside of mapped flood hazard areas. So a lot of my previous research is kind of focused on this issue and thinking about this issue. So nationwide, about 28% of damages and 33% of insured loss have occurred outside of floodplain areas, outside of designated floodplain areas. And in some areas, these rates are really quite a bit higher. So parts of Harris County are a great example. We've seen in some communities, you could be seeing 3/4 of losses occurring outside of floodplains. We're also seeing that the rates are growing fastest in urban and coastal areas. And it's worth pointing out two things. One is that insured losses don't present a very comprehensive picture of the losses that are associated with flooding. They don't account for uninsured loss, and uninsured loss is a big piece of the puzzle. Another thing is that many of the sources of flooding are unmapped. So the floodplains, the FEMA floodplains, the regulatory floodplains represent coastal or riverine flooding, not combined flooding, not infrastructure failure. They also don't consider pluvial or urban flooding. I mentioned combined flooding or high tide flooding. So there are many types or many other ways that floods can occur, and the maps don't represent all of them. And the reason that this is all critically important is that our primary tool to defend against flooding is our understanding of where these hazards are. So we cannot adapt, we can't mitigate, we cannot design for the future if we don't understand where the hazards are or how they're changing in space and time. And hopefully Alyssa forgives me for pulling this from her recent paper submission, which is coming out soon, but there's sort of the need to think about creative ways to map flood hazards at large scales that may be more accurate and can be rapidly updated as more information becomes available, because our current way or our current methods for mapping flood hazards not only don't capture all of the flooding, but they also are often outdated, and they're very computationally expensive and man-hour expensive to produce. So along those lines, kind of some of the things we're thinking about for North Carolina and the things my group is working on. This picture is a little outdated. We have a couple other people, and some people have left and graduated, but my group's really focused on trying to understand the dynamic interactions between natural, social, and engineered systems and how they're driving flood risk across space and time. So you kind of saw an inkling of that with the work I had done on Harvey, but we're also thinking about this here in the state of North Carolina. And just to showcase quickly a few things, and then I'll stop talking. My master's student Hunter is looking at the Neuse River Basin and working with Kathy Dello to look at future climate and also projected development in the Neuse River Basin and how it might impact floods throughout the river basin. My PhD student is thinking about compound flooding right now in the Neuse, but we're hoping to do this for the whole coast of North Carolina. We're particularly interested in trying to understand how climate change has changed the interactions between riverine flows and coastal storm surge, and how this relates to community flood risk over time. This is an undergraduate project. Sarah actually recently graduated. It's a great undergraduate project, and we're hoping to find somebody else because it's a fun project to learn to code, and it also we're seeing some really cool results, but we're looking at multi-decadal trends in design floods throughout the Southeast and trying to understand what might be driving them in certain locations. And then finally, my postdoc recently published this paper looking at uninsured loss or predicting uninsured loss across the state of North Carolina based on recent events, so the risk of uninsured loss annually. And the reason that I think I'm really interested in uninsured loss at the moment, you've heard me say it a couple of times, is that uninsured loss, I think, is a significant indicator of some of the equity issues that we have around flood recovery. So those who are uninsured have less capacity to recover immediately after a flood event. They may also represent people who have less access to capital. And so their recovery is slower. And I'm working on a collaborative project with some people at the Center on Financial Risk and Environmental Systems to understand how this uninsured loss can cascade through financial systems and affect lenders, local government, and property owners, of course, as through the recovery process. And we're seeing very disparate effects on different types of communities. So comparing urban and rural and those living inside the floodplain and those living outside the floodplain. And so this work I'm really excited on, but it's hot off the press, so I'm not going to talk about it that much today. And then finally, and this is my closing slide, we were recently funded through NOAA RISA on a new climate, health, and equity in the Carolinas project. We're working closely, or our aspiration is to work closely with communities to understand how they're impacted by climate change and to also think about adaptation together with communities. And I am working with a couple of people at NC State who I saw on this call, Jennifer Runkle, Louis Rivers, and Kathy Dello, and Jane Harrison, but also we have partners at NCCU, Furman, South Carolina State University, and the Museum of Life and Science. And so this is a new emerging project that we're really excited about. I'm going to leave it there. I feel like I threw a lot of things out there at the very end, and I would really welcome questions and discussions on any aspect of the things that I presented on.
Thank you very much, Tony, for fascinating presentation. There was a lot of interesting things to digest. So, okay. So please, for those of you that would like to ask a question, please post it into chat. And while we are waiting for questions from the audience, I have one question. I was wondering about the stream buffers. As you know, like here in North Carolina, we have mandated stream buffers in many communities. I was wondering how it was in the in Houston area, whether there have the stream buffers. I haven't seen any trees along on those pictures that you had there, and whether that was included in some of these recommendations, and whether the models would indicate that they are actually useful. Yeah, if you can elaborate a little bit about stream buffers.
Yeah, so the models that I'm running don't take into consideration vegetation beyond the soil parameters and the land use, land cover as a function of imperviousness and the soil infiltration. So the models don't explicitly represent any sort of trees, although I could imagine we could fiddle a little bit with those infiltration parameters to sort of implicitly get at them. In Houston, it is an interesting question. There are not, so live oak are definitely a type of tree that are in Houston native. And historically, trees grew like it's a severe climate, right? So historically, the trees that grew along those bayous, but because of development, I would say, if I'm thinking about my neighborhood in Houston, there's not all that many trees along the stream corridors. That the comparison between Buffalo and Braze, the trees in Braze Bayou are very far from the stream because of how channelized that system is. In Buffalo Bayou, there's been a lot of tree planting along the stream corridor, but I would also say that perhaps this has been a policy over time to remove the trees to allow, like as part of the channelization strategy, to allow the water to move more freely in those systems. But I don't feel like Houston is a very forested area. So after moving to North Carolina, I would say there's not a lot of trees in Houston. So hopefully that answers your question.
Yes. So no recommendations for them to grow more, but maybe the trees wouldn't survive there.
Yeah, and I do think that there has been, so Buffalo Bayou, that buffer zone has been turned in, they just spent $50 million making it into a park space. Granted, it floods all the time and they're constantly like cleaning it up and fixing it. But there has been a lot of tree planting along Buffalo Bayou, but I don't know to what extent that's been considered in the models at all. But
okay, thank you, thanks. So do we have any other questions?
I have a question.
Yeah,
That was an awesome presentation.
thanks. Sorry for stealing your figure.
Oh, no worries. I was just curious if you had any suggestions for calibrating a model to capture peak flow as well. And I know you like kind of touched on that at the beginning with the VFlow model. So I'm sure it's model dependent. And we've had this conversation before about how there's a lot of different models to do these sorts of things. But yeah, I guess in your experience, what have you found to be particularly useful, like gauge selection or time period selection and so on?
Yeah, so the models that I have run in the past tend to be very event-based. So we're usually modeling, we're pulling like a very high resolution rainfall estimate, and we're running short periods on the order of hours to a month. So I haven't done a lot. So personally, I have not done a lot of modeling that looks across like longer time scales, although it's something I'm starting to engage with tentatively. But in the Houston system, or like a starting place for me has always been like sensitivity analysis, right? So scaling your parameters and seeing how your model responds to those. And in Houston, channel roughness was always an extremely sensitive parameter in my model. And I don't know exactly what you're doing with respect to calibration, but I do think it's important to, I don't know to what extent you also need to calibrate to volume, but when we do event-based modeling, we're often trying to get both the volume and the peak correct, and the timing, of course, but understanding the sensitivity of your model to each of those parameters is really helpful in trying to identify the space in which you can calibrate. And the model that I've played with allows you to sort of scale those calibration factors really, really easily. So it's very model dependent, but my thing would be like, don't forget about the other parameters that you care about for your system. And also, if you're concerned about flooding, you might be most concerned with peak flow. If you're considering more like the ecological side, volumes might be more important. So you can also kind of prioritize certain properties of your watershed.
Awesome. Thank you. That's super helpful.
I think Alberto, you have a question.
Good afternoon. Hi, my name is Alberto. I'm from the Biosystem Engineering Department of the University of Costa Rica. I have a special question. Well, first of all, amazing presentation, very insightful. My question goes regarding the urbanization pattern. As you mentioned before, that one point that can be used is the change the patterns. But what kind of patterns can be used or can be changed for future models for working and to help the flood resilience in that part of Houston?
Yeah, so that's really interesting and something that I didn't have capacity, time, whatever we want to say, to get into. There's actually some work that has been done by Avantika Gori, who has now shifted more into the compound flooding world, but her master's thesis looked at how to represent small scale regulation around how much on-site retention was required. So the modeling that I did, we changed roughness, we changed infiltration patterns, but we assumed that if we could represent Harvey in 2017 and we could represent that 1935 storm, we did fine on the urbanization. In reality, and Harvey was also a really big event, right? In reality, there are lots of regulation in Houston that have come into play probably in the 90s and later around on-site retention, and we don't usually consider them in our models. And so Av's work, and her paper was, I think it's Gori, Blessing et al. In 2019. Her work really looked at how do we represent that retention on site and what is the optimal amount of retention you might need on site to offset the development. And I think that's a really interesting modeling question, but also policy question. So that's one part of my answer. And the other part of my answer is one of the things that I'm really interested. So Houston is fairly urbanized already at a very, very large scale. So we're probably thinking a lot about retrofit in Houston on sites. But in terms of new development, I think there are interesting connections between the hydrology side of this and sort of the land use modeling side of this. And so I'm kind of looking to this group on the future side, because I think you can think about setting policies that require certain amounts of green space to remain open, et cetera, and then looking at how that plays out in your hydrologic model. And in the Houston area, some of the areas that are not yet developed that should not be developed if you can avoid it is upstream of Addicks and Barker, there's a coastal prairie. It's a pothole prairie. And if that gets developed, it's going to have very, very significant impacts downstream. And so that's an area that hasn't yet been developed. There's also old rice fields that are sort of interestingly terraced right now. And if those terraces get removed, it will probably cause a lot of downstream flooding. So all of that's discussed in Avi Gori's work in her paper as well. So I don't know if that answered your question. I just sort of rambled about a bunch of things, but there are definitely a few key areas that have not yet been developed that are providing significant storage right now to downstream effects.
Okay. I also have a second question is, for future work, you consider using like climate change scenarios for the IPCC?
Yeah,
Or
so
like
the
for
work that
long-term
Hunter,
decision making?
yeah, the work that Hunter is doing in my group, right now, we're not doing a lot around pathways or decision making. We're kind of just taking the climate models and running them into the future. But I do think there are some interesting coupled human system type papers that actually consider the feedbacks of some of these things and look at adaptive pathways. I'm not doing it right now, but it's all exciting.
Okay, thank you.
Yeah, okay, thank you. Laura Velika has a really good question. Laura, do you want to ask it directly? Okay. Okay, okay, she doesn't have a microphone, so I will read it. Okay, so she's curious if you have had a chance to look at the sensitivity of the model to scale and resolution. So for example, in terms of narrow, small areas of riparian or bayou forests that may remain, but may not be visible at some scales. For example, depending on the land cover or soils data sets, and how that may vary and impact results or estimates across these larger watersheds with complex land use and hydrology.
Yeah, that's a great question. And I actually took out my limitation slide because I was nervous about time, but I had a slide at the end where I mentioned that we didn't take into consideration stormwater infrastructure in the like subsurface sense, but also the Houston area has a lot of roadside ditches, so open swales. And we also, yeah, I meant to look up what the scale of the model was, the resolution of the model was at the time, but I have not personally looked at the sensitivity of the scale or the resolution of the model to those things. I do think connectivity in Houston is really, really important. I think part of the urbanization, as urbanization has happened, we've actually increased connectivity in a lot of ways in the city of Houston, both overland and in the subsurface network. And that's partially, I think the model we did for Bray's Bayou doesn't consider that, but I know that that is contributing to the flooding seen in Bray's Bayou as well because of the connection between the storm sewer network and Bray's Bayou. Another limitation of the work that I had done or that I showed today was that we didn't consider pluvial flooding, which is related to that as well. I've run a model since then and it's published. But some of those questions I think are still out there. So I haven't looked at it, but I think you're totally on the right track for asking that question because I do think it's something we need to understand better.
Okay, thank you. Thank you. Do we have any, there is like last question because we are starting to be over time. Does anybody?
I would like to ask a question if that's okay. I'll try to make it short.
Okay.
Wonderful presentation. Thank you so much, Tony. So you had the great opportunity that your research directly informed policy in Texas. I was wondering, how do you feel about the landscape here in North Carolina?
So that's interesting. So I have really enjoyed being in North Carolina. I think I arrived at a really interesting moment in time. I got to work on a North Carolina policy collaboratory project on post-Florence flood resilience. So I felt like I was stepping out of one flood and into the next flood. And it's been very interesting to work in North Carolina because it is a little bit of a different landscape. I think there is a lot more, from a cultural standpoint, the environment is valued in North Carolina in a way that's very different from it being valued in Texas. And that, I think there are already much stricter regulations on what development looks like here, stream buffers, thinking about, especially around water quality. There is a lot of regulation in North Carolina to an extent that I didn't really feel in Houston. So that the sort of the landscape in which you're working in is really different. But I also think that there's just as much potential to influence policy here as there is in Texas. And I would say the politics of policy are not that different between the states. So I've really enjoyed being here. I will say I'm COVID new, so I haven't really gotten out of my house all that much in the last 2 years. So I don't know if I can provide a great perspective on making changes in North Carolina yet, but I am excited to be here, and I do really like the work that is going on here around the state. I think there are super cool collaboration opportunities as well. So hope that answered your question, but yeah.
Absolutely.
Awesome.
Okay, thank you. There is just a small comment in the chat, so you can, Tony, you can read it. I think it's a good point, and I think you addressed it to some extent already. So thank you, John, for that comment. And thank you all. Thank you, first of all, Tony, for that great presentation and leading a really great discussion. It's a topic that we are all very interested in. And thank you all for participating in today's Geospatial Forum. And we hope to see you next time at this forum. Thank you all. Thanks.
Thanks for the invitation. I really enjoyed it.
Thanks a lot, Tony. Appreciate it.